Okay, so we start the class. This example, we want to determine the force in each cable. Okay, so from the figure, we can see there are 3 cables, and excluding this one, there are 3 cables, and used to support 400 Newton crate here. Okay, so we know here is 400 Newton, and then using to solve this equation, we have 3 unknown. Okay, 3 unknown is the force for, okay, I define as AB, and force AC, and force AD. Okay, there are 3 unknown. So we can present AB, AC, and AD using Cartesian vector. But to work out Cartesian vector, we should present the result using force vector. But force vector, we have to find out unit vector for each direction, from A to B, from A to C, and from A to D. Okay, so we can rely on position vector, okay, from for 3 different directions, and then divided by scalar, okay, divided by length. So we can work out a unit vector for each. Then unit vector times force scale. So we present each force using Cartesian vector. Then 3 different force. Okay, here are 3 different force. 3 different force. Okay, we present. So 3 unknown parameter. And for x component, this one doesn't have x component. Okay, so for x component, summation of them equal to 0. Okay, then for y component, summation of them equal to 0, and z component, summation of them equal to 0. Okay, so that's this part. Okay, summation of them equal to 0. So we can work out 3 different unknown parameters. Okay, then 3 equilibrium equation with 3 unknown. So that means we can work out the value for each. Okay, so that's a general concept. But here, from our observation, this system is a symmetric system. Okay, symmetric plane is this way, along x-axis. Okay, symmetric plane is YZ plane. No, not YZ, XZ plane. Okay, so negative y and positive y. Okay, this system is the same. So actually, from our observation, we should know AB and AC in terms of magnitude, they should be the same. Because symmetric system, they should have the same magnitude. Clear? So finally, as a reason, due to its a symmetric system, B and C will have the same magnitude. Okay, but we look at the component in detail. For Y, so Y is regarding J component. So for J component, FC is positive, but FB is negative due to their opposite direction. Okay? Okay, next example. Determine the tension in each core used to support 100 kilogram crate. Okay, this one is 100 kilogram, and therefore have to change a unit. Change a unit. Okay, so from our observation, there are 2 cable and 1 spring. Okay, we can still rely on position vector. Position vector, okay, to represent each one. And then when we have position vector, we can have a unit vector. Okay, then summation each direction, so equal to 0 to obtain equilibrium equation. Then we can rely on equilibrium equation to work out FB, FC, and FD. Okay, here FD, okay, FB is along x-axis, so only one direction of component along x-axis. Okay, positive is this way. This way is positive. FC, here we work out a unit vector rely on the degree alpha, beta, gamma. Okay, cosine alpha is a unit vector for x direction. Okay, cosine beta, cosine gamma. So we use degree to work out unit vector. Okay, so we can represent FC using Cartesian vector. Okay, based on this equation. Then FD, this one, we use the position vector divided by scalar. This part is unit vector. Unit vector. So we have unit vector. This part divided by this, so we can work out this component. This part divided by this, which is this component. So that's a unit vector. You can ask me. That's fine. Which part you feel confused?
No, I'm confused of the picture sometimes.
X direction this way,
Oh,
Y is this way,
Okay.
and Z is this way. So for FB is along X,
Okay.
because all code connected to point A.
Okay.
Okay, then FD we rely on the degree. Degree with X is alpha. Degree with Y is beta. So alpha, beta. Okay.
Great.
Okay, then FD we use the unit vector. So represent FD using Cartesian system. Okay, then the weight, okay, which is downward, so it gives negative. And then summation all of them should be equal to 0. And we have 3 different directions, x, y, z. Okay, summation of them equal to 0. So we have 3 different directions, x, y, z. Individually, okay, each equation should be equal to 0. So based on the information, we use these 2 first. Because these 2 only have 2 unknown parameters. So we can work out FC and FD first. Then we know FC and FD put into first one. So we can work out FD. Clear? Okay, practice question. The 3 cable, okay, AB, AC, AD, okay, 3 cable, used to support 40 kilogram flower pot. Okay, this one, flower pot 40 kilogram, and which means we have to change the unit. And determine the force developed in each cable. Okay, personally, if I solve this question, I will use my observation first. So this one is downward. So AB and AC, which is horizontal, so both of them do not provide a support to this because it's vertical. So vertical support comes from this. Do you remember when we use that's a two-dimensional? We use a triangular relation, and due to they are right triangle, okay, they are right triangle. So that means we can directly use the ratio of it. So okay, so we start the class. This example, we want to determine the force in each cable. Okay, so from the figure, we can see there are 3 cables, and excluding this one, there are 3 cables, and used to support 400 Newton crate here. Okay, so we know here is 400 Newton, and then using to solve this equation, we have 3 unknown. Okay, 3 unknown is the force for, okay, I define as AB, and force AC, and force AD. Okay, there are 3 unknown. So we can present AB, AC, and AD using Cartesian vector. But to work out Cartesian vector, we should present the result using force vector. But force vector, we have to find out unit vector for each direction, from A to B, from A to C, and from A to D. Okay, so we can rely on position vector, okay, from for 3 different directions, and then divide it by scalar, okay, divided by length. So we can work out a unit vector for each. Then unit vector times force scale. So we present each force using Cartesian vector. Then 3 different force. Okay, here are 3 different force. 3 different force. Okay, we present. So 3 unknown parameter. And for x component, this one doesn't have x component. Okay, so for x component, summation of them equal to 0. Okay, then for y component, summation of them equal to 0, and z component, summation of them equal to 0. Okay, so that's this part. Okay, summation of them equal to 0. So we can work out 3 different unknown parameters. Okay, then 3 equilibrium equation with 3 unknown. So that means we can work out the value for each. Okay, so that's a general concept. But here, from our observation, this system is a symmetric system. Okay, symmetric plane is this way, along x-axis. Okay, symmetric plane is YZ plane. No, not YZ, XZ plane. Okay, so negative y and positive y. Okay, this system is the same. So actually, from our observation, we should know AB and AC in terms of magnitude. They should be the same because symmetric system they should have the same magnitude. Clear? So finally, as a reason, due to its a symmetric system, B and C will have the same magnitude. Okay, but we look at the component in detail for Y. So Y is regarding J component. So for J component, FC is positive, but FB is negative due to their opposite direction. Okay? Okay, next example. Determine the tension in each core used to support 100 kilogram crate. Okay, this one is 100 kilogram, and therefore we have to change a unit. Okay, so from our observation, there are 2 cable and 1 spring. Okay, we can still rely on position vector, okay, to represent each one. And then when we have position vector, we can have a unit vector. Okay, then summation each direction, so equal to 0 to obtain equilibrium equation. Then we can rely on equilibrium equation to work out FB, FC, and FD. Okay, here FB, FB is along x-axis, so only one direction of component along x-axis. Okay, positive is this way. This way is positive. FC here, we work out a unit vector rely on the degree alpha, beta, gamma. Okay, cosine alpha is a unit vector for x direction. Okay, cosine beta, cosine gamma. So we use degree to work out unit vector. Okay, so we can represent FC using Cartesian vector. Okay, based on this equation. Then FD, this one, we use the position vector divided by scalar. In this part is unit vector. So we have unit vector. This part divided by this, so we can work out this component. This part divided by this, which is this component. So that's a unit vector. You can ask me. That's fine. Which part you feel confused?
No, I'm confused of the picture sometimes.
X direction this way,
Oh.
Y is this way,
Okay.
and Z is this way. So for FB is along X,
Okay.
because all code connected to point A.
Okay.
Okay, then FD we rely on the degree. Degree with X is alpha. Degree with Y is beta. So alpha, beta. Okay.
Great.
Okay, then FD we use the unit vector. So represent FD using Cartesian system. Okay, then the weight, which is downward, so it gives negative. And then summation of them should be equal to 0. And we have 3 different directions, x, y, z. Okay, summation of them equal to 0, but we have 3 different directions, x, y, z, individually. Okay, each equation should be equal to 0. So based on the information, we use these 2 first. Because these 2 only have 2 unknown parameters. So we can work out FC and FD first. Then we know FC and FD put into first one. So we can work out FB. Clear? Okay, practice question. The three cable, okay, AB, AC, AD, okay, three cable, used to support 40 kilogram flower pot. Okay, this one, flower pot 40 kilogram, and which means we have to change the unit. And determine the force developed in each cable. Okay, personally, if I solve this question, I will use my observation first. So this one is downward. So AB and AC, which is horizontal, so both of them do not provide a support to this because it's vertical. So vertical support comes from this. Do you remember when we use that's a two-dimensional? We use the triangular relation, and due to they are right triangle, okay, they are right triangle. So that means we can directly use the ratio of it. So I know the vertical component should be the same as this magnitude. So we rely on the ratio. We can work out total force for this component. Okay? So this force AD has X, Y, Z, three different directions, three different components. But AC is only X direction, and AB is only Y direction. Okay, so this one is only Z direction. So that means each of it will be the component X, Y, Z for this one. Okay, so from observation, we can quickly solve the magnitude of each. Of course, if you want to represent using Cartesian system, you should work out a unit vector for each direction. Okay, next example, the shear leg, the ring, is used to hold a 200 gram net of fish onto the dock. Okay, shear leg. Okay, I saw shear leg should be these two, AB and CB. So determine the compressive force along each of leg, AB and CB, and the tension in the winch cable DB. Okay, cable is this part. So assume the force in each leg act along its axis. Okay, so that means you see, fish is loading. Okay, vertical loading. So that means Z direction. Okay, negative direction. And all three forces from cable and two legs, they are all connected to this point. Okay, they are all connected to this point. So also fish loading also connected to this point. So that means we consider force equilibrium at this point. At this point, we can work out the individual condition, and then we should use unit vector to work out each force. Okay, including the cable and leg force. Okay, we use the unit vector. And unit vector, how do we work out? We use the position vector divided by its length. So we can work out unit vector. So summation all force together, including two legs, one cable, and fish loading, summation of leg equal to 0. So it will go back to this situation, summation of leg equal to 0. So individually, x component equal to 0, y component equal to 0, z component equal to 0. So that means this equation, this equation, this part is non-information. So we have three equilibrium equations x, y, z, and then we solve three unknown information. Okay, clear? But keep in mind, this one is cable. Okay, this one is cable. So only tension. And due to remember, we talked about. I saw yesterday I mentioned tension is lift away the point. Lift away the particle. Remember? Yesterday or last week, I mentioned tension is the condition, the force we lift away the particle. So if we look at this particle is this joint. So tension lift away. So that means this force is for z direction is what? Is downward. Okay? This force is also downward. And this system is also symmetric system. We agree with that? Symmetric system. So that means these two legs should be upward. Okay, upward. That's the reason. It's compression. Okay, so if you have to determine the direction, you should consider the nature of material. So if here is tension, here is also a downward force. So these two legs provide the force upward. They are this system is symmetric. Symmetric, so that it's I shouldn't say possible. It must, these two legs must provide the same contribution. Okay? But if the loading is not symmetric, okay, we cannot judge using this kind of observation. Clear? Only symmetric system. Okay, symmetry, last thing, this one is compression, so this one is also compression. But if it is not symmetric, we cannot judge using this. Okay, so we finish chapter 3. And my TA remind me to give assignment, question, and the question should be uploaded tomorrow.
How?
Okay, chapter 4. We are talking about force system resultant. I will say chapter 4 is an extension from chapter 2 and 3. We will use a combined concept to solve the chapter 4 problem. Theoretically, chapter 4 is a very long chapter. So generally, from my previous experience, if schedule goes relatively smooth, so it's possible we finish chapter 4 and have the first midterm exam. Okay, but if the progress is slower, so probably somewhere in chapter 4, we should have the first midterm exam. So I quickly check the time schedule. So this week is which week? Week 4 or week 5? We start. I saw our course start from 20 in February. Okay, first week, second. Okay, this week is 5th week. Okay, we have first midterm on 18th of April. Okay, 18th of April. You still have almost one month, almost. So don't worry too much. University has holiday finished on 5th of April. Am I right? Finish on 5th of April. Okay. Okay. Anyway, we use 18th of April as the first midterm exam. Okay, moment of a force using a scalar formation. And so to work out the moment, the tendency to rotate is called the moment of a force. Okay, the moment of a force. That's F. So we use this force times by distance, but the distance should be perpendicular. Okay, force and distance should perpendicular to each other. So we use this one to work out moment. And this kind of moment we also can call as a torque. Okay, so torque, the simple application you can imagine is like you try to control a steering wheel. Okay, steering wheel. So we control direction, and middle of steering wheel is the main controller, but our handle which is bigger. So this is a force applied to the same as the force we apply to steering wheel. Okay. Okay. Practically, it is possible the force we apply has certain degree with the level up. Okay, it's possible. We have certain degree here. Okay, and therefore, based on this situation, we should use the correct distance. Correct distance. So I call it as the modified distance. So modified distance to make the force direction with our reference point. Okay, rotational center has the direction perpendicular to the force direction. So you, based on this right triangle, this distance, we use d sine theta. Okay, d sine theta. Real right triangle is here, theta is here. So sine theta is this distance. Okay, for this distance, how to work out? All okay for you? D sine theta. So we work out the perpendicular direction distance. Okay, then if we apply the force pass through our reference rotational center, it will not provide any moment. Okay, because in terms of distance, which is 0. Okay, because distance must be perpendicular direction to your loading direction. This loading direction pass through the rotational center, so moment equal to 0. Okay, then I want you to remember a little bit here because this concept will be applied in future slide. So remember this right triangle d sine theta, because later on we will use some of this information when we do some derivation. Okay, magnitude for a moment, we use force times by level up. Okay, distance d is level up. Okay, and we also can call it as the moment up. So, which is the perpendicular distance. And then we work out the moment, the unit will be Newton times by meter. Okay, remember for our calculation, we still need to maintain which is SI unit. So Newton and meter, both of them are SI unit. Okay, direction defined by its moment axis, which is perpendicular to the plane that contains the force and level up. So using this one as an example, okay, force and level moment up, both of them are on this plane. Okay, are on this plane. So we use force distance, which can form a plane, then the direction perpendicular to this plane, which is the direction of moment. Okay, here we will use cross. Remember right hand rule. Okay, right hand rule. So we can use F, forefinger toward F first. Okay, then to the level up. Okay, from force to level up. So direction, this direction is the moment direction. So it's like here, F, then toward the level up. Okay, toward the level up. So give a distance. Not distance, give direction. So this is moment direction. Okay? So for the moment direction definition, clear for you. So of course, due to three-dimensional problem, we can have different direction of moment. Can you imagine? Because we have different plane. Okay, so that's the main content this chapter. We have to learn from 2D first, and then later on extended to 3D condition. So force, then curve to the level on direction give us the moment direction. Okay, that's the same concept applied to whole chapter. Okay, then resultant moment, of course, practically we can have many different force. Okay, many different force, many different level up. So we can use summation of the moment. So to work out the resultant moment. Resultant moment. So resultant moment, this kind of system more frequently to be seen in vehicle, because vehicle have lots of structural elements. They all have different loading. So we want to know those loading and moment combination. Okay, resultant moment, resultant force. How much is the influence to each element? Okay, maybe you have a little bit difficult to imagine what's the problem. For example, in vehicle system, civil structure is relatively simple. But for vehicle system, maybe this element have certain vibration. This element also have certain vibration. This element has certain vibration. Okay? So they will all cause different force, different moment. But for example, if we want to design this element, the other elements are moving, have certain vibration and moment. So we have to conclude the summation of them to this structure, and then we are designing this structure individually. Okay, so that's a vehicle situation. Any accident? Now popular to hear this. Okay, so we can use this formula to work out the summation of moment, and then positive moment we define as counterclockwise, positive. Then clockwise we consider which is the negative moment. Okay, so for this point, F1 give positive counterclockwise. Okay, then F2 give clockwise, so negative. And F3 also counterclockwise. So F1 and F3 give positive component, but F2 give negative component. Clear? And this kind of consideration highly rely on which point you are considering. Okay, if you consider this point, everything we calculate using this point. But for example, I move the point to here. Okay, I move this point to here. F1 will give negative component because F1 give clockwise. Okay, I'm talking about I move the reference point to this point. So F1 give clockwise. So F1 become negative. Okay, so this kind of consideration rely on the point position. Okay, where is the position? So every calculation determined based on reference point. Clear? So here have some practice. Example 4.1. So for this case, determine the moment of above point O. So reference point is point O, and force is 100 Newton. Moment arm is 2 meter. Okay? So our calculation is 100 times by level arm 2 meter, and give us positive because reference point is here. Oh, so sorry, it's not positive, it's negative. Clockwise is negative. But if we show the direction, we don't need to show it's positive or negative. Okay, we always use positive because we show the direction. So 100 times by 2 and give the moment clockwise 200 Newton meter. Okay? Very simple application. So more advanced, I will not say those practice questions are difficult, but we just need to judge the direction and particularly level up judgment is important. So we look at question B, loading 50 Newton toward left, and to reference point O, level arm is 0.75. Okay, perpendicular distance, perpendicular to the force direction. So level arm is this one. Clear? So, do you think it gives clockwise or counterclockwise moment? Say loudly.
Clockwise.
Yes, clockwise. Okay, because the reference point is here. Reference point is here. And this force, okay, is 10 to here. So it gives the moment rotate like this. So which is clockwise. Okay, clockwise, then calculation shown here. And we show the moment direction. Okay, next one. We look at question C. Force 400 Newton this way. Then level arm is this. We consider reference point. Okay, level arm is this because we have to work out the distance perpendicular to the force. Okay, force direction is this one. So distance perpendicular, which is this distance. And here is inclined. So we have to work out its horizontal component. So 2 cosine 30 horizontal component. So moment arm is 4 plus this component. And do you think this moment system provide positive, counterclockwise or clockwise? Yes, also clockwise. Reference point is here, so downward also clockwise. Okay, next one. Question D. And reference point still here. Loading is here. So level arm is this part. Okay, level arm is this part. So we have distance here, length here. So we work out this component, which is sine 1 times by sine 45 degrees. Okay, so that's a level arm. But reference point is here, loading direction is here. So it gives counterclockwise moment. Okay. Next, force here, and we have many different dimensions. but we care about here is the reference point. So reference point link to loading direction, and perpendicular to this loading direction, which is level 1. So level 1 is this. Okay, so that's the reason. Level 1. 4 minus 1. Okay, so which is this. Okay, then this force also give moment counterclockwise. Clear? Okay, and later concept is more advanced application. Okay, next example. Determine the resultant moment of the 4 forces acting on the rod. Okay, there are 4 forces. 1, 2, 3, 4. On the rod. Okay, then we care about the moment for point O, so that's the reference point. Okay, then for calculation, we work out the resultant moment, so we apply this equation. Then we have to define positive moment direction. So counterclockwise is positive. Okay, counterclockwise. So we look at each force. So for reference point O here, this 50 Newton force, level 1 is this one. Okay, force direction, level 1, perpendicular. Then positive or negative? Negative, yes, because it's clockwise moment, so negative. Okay, then we look at second force, 60. This force pass through point O, so there is no moment on. So contribution is 0. Okay? Next force. Okay, I look at 20 first. Okay, 20. 20 level on is this distance. So we know this part is 3 meters. Okay, and then we know the angle is here. So we want to know this distance. So that's a sine 30 degrees. Okay. Level on is sine 30 degrees. Okay, and for this loading condition, 20 Newton, clockwise or counterclockwise? 20. Huh? Counter, yes. So which is positive. Okay? So level 1 is this part. So 3 cosine 30 is level on for this distance, and plus 4. That's a 4 is here. 3 cosine 30 is here. So that's a level on for 40 Newton. So 40 Newton also clockwise moment, so which is negative. So summation, that means plus them together. So finally, we work out the moment is negative 334 Newton meter. So if we show negative, that means clockwise. Okay, if we don't show negative, we use direction. So this one we use a positive value. So 2 ways to show the result. Clear? Okay, then this part, this section, we go to discuss cross product. So last time we talked about dot product. So dot product is the final outcome is purely scalar. Remember, A dot B equal to AB cosine theta. Okay, AB cosine theta. But right now we work out the cross product. Okay, cross product is two vector. Give the third vector. Okay, A cross B give us a C vector. Okay, so we can represent like this. So we read this part C equals A cross B. Okay, so we use A cross B got C vector. So in terms of magnitude, C is AB sine theta. Okay, sine theta is important. Sine theta. This part, this concept will be applied to here. Okay, I mentioned sine theta. Okay, later on for our derivation, we will try to find the connection from here. Okay. Okay, so for cross product, we still apply our right hand. So A cross B, A cross A direction toward B direction. Okay, A cross B give us third direction. So it satisfies our previous concept. When we work out the moment, remember, force, then toward distance, give us the third moment. So cross product help us to deal with this kind of a vector problem. Okay, so that's the reason we introduce this part first. Then we tell you cross product can be applied to this part. Okay, then the sum direction is vector C. So of course we have the third direction. We can work out like the unit vector of each. So the concept is the same as chapter 3. Okay, so AB sine theta is scalar, remember? But if we use vector A cross vector B, sorry, here should be this one. This one should be non-italic because that's a vector. Okay, so vector A cross vector B give us vector C. So which is AB sine theta, which is scalar. Scalar times by unit vector. Okay? Clear? So far. Okay, and please turn off the video recording. Hello. Turn off.
Okay.
Start next class. Okay, I saw this one. This part we finish. Okay then. For cross product, due to it has directional effect. So A cross B does not equal to B cross A because B cross A it become inverse, opposite direction. So B cross A. So so it becomes opposite direction. So we cannot change each other. But we can present our result A cross B equal to negative 3 of B cross A because they are opposite direction. Okay? And then, so if A cross B give us positive C, so B cross A give us negative C, negative, positive. Okay, so here is negative. Clear? Okay, then law of operation, if we have certain magnitude outside the cross product, but we still can distribute it, this A to any place, because A is only scalar, only value, nothing to do with calculation. So we can change the A position, and also we can distribute it. If we have an addition vector here, so we can distribute it here. So A cross B and plus A cross D. So we can use this one. Okay. So for if we use the unit vector to explain cross product, so I is x direction, j is y direction. Okay, I x, j is y. So cross product give us unit vector for z direction. So give us k. Okay, so cross product is I is 1 in terms of scalar. They are unit vector. So this part is 1. This part is also 1. Then sine 90 degree. Sine 90 degree is also 1. Okay. 90 degree comes from all three axes. They are perpendicular to each other. So sine 90 is 1. So I cross j, I this way, cross j, I rotate to j, give us k direction. The same approach, j cross k, give us positive I. Okay, I cross j give us positive k. J cross k give us positive I this way. So k cross I give us positive j. So this is how do we define positive direction? Okay, positive still use right hand. So how do we define positive direction? I cross j, positive k. J cross k, positive I. Okay, then k cross I, positive j. You can practice using your hand. Okay, if you are not sure, make sure you use the right hand. That's more important. Okay. So that's how we define positive axis. So that's the reason we use the right hand rule. Okay, so that's a cycle. Okay, to get positive value. This counterclockwise is positive value. So if our cross product is clockwise, so it gives us negative value. Okay, you are not necessary to remember this, but I feel if you remember this coordinate system, this coordinate system, you can use your right hand, okay, to find whatever you want. I can tell you, although I graduate from undergraduate for more than 20 years, but I still remember to use my right hand to define the coordinate. So as long as you remember the coordinate system properly, okay, then you don't need to remember the further operation, okay, make your memory make operation more easy. Okay, that's the same as I mentioned. So I cross j gives us k, but I cross k gives us negative j, okay? And I cross I is 0 because sine 0 is 0. Remember from previous calculation, sine, if two vector has the same direction, so its degree is 0. So sine 0 is 0. So we don't need to work out that. Okay, then it gives you the positive and negative meaning. Clockwise is negative. Counterclockwise here is positive. Okay, then for more detailed operation, okay, calculation, two vector A and B, A cross B. So A can be represented using this form, Cartesian vector. B also can be represented using this form. Okay, so we use first part, AX times by this part. Okay? Then AX times by this part, cross product, okay? A cross BX, AX cross BY, AX cross BZ. Then we show like this. Okay? We show like this. And first part, I cross I, 0. Okay, this part 0. I cross J is K. Okay, I cross K is negative J. Okay? I is this direction. K is this direction. Yes, I cross J gives us negative Y direction. So here is negative. So the same as first line, that we use the second component cross each. So show like this. Okay, then this part is gone, which is 0. Okay, then the third one come from here and work out the third line. And this part is gone. Okay, then we rearrange the whole component. Which one give us I? Okay, I. First one didn't. First line didn't. So I only come from second line and third line. So they should be from K and J. Okay. So K and J, J cross K is positive. Okay. J cross K is positive this way. So that means K cross J is negative. So this component is positive. And okay, this component is negative. Okay, then for J component, so it comes from I and K. J component comes from I and K. So look at first line. I cross K. I is this direction. K is this direction. So I cross K is negative. So this part gives negative. negative. Okay, but we have negative here. So this part already include a negative meaning in it. Okay, so Ki give us positive meaning. So negative, so it become positive. Okay, negative, it become positive. So which is this component. Okay, then for K direction, so it comes from Ij. Ij is positive. So Ij is positive. Okay, so that means Ji is negative. So negative meaning. So this complicated calculation we rearrange. Finally, we got this component. Okay, not very easy to remember, but anyway, we try our best. Later on, we'll show you how do we remember this kind of calculation related easier. Okay, we use this form to remember if two vector cross product, so we list like this: ijk x, vector A component, vector B component. So you must list like this, okay? X, they are I direction, X direction. So you cannot list, okay, Bx is here. It's not correct, okay? We must follow this form. Okay, we must follow this form. So, when we work out I component, okay, so we only leave this part, okay? So, because for I cross I there is no meaning. I cross I there is no meaning. So, we delete this part. Okay, so we have those components left. So for our calculation, we work out like this. Okay, AY, BZ minus AZ, BY. Okay, AY, BZ minus AZ, BY. Okay, then for the second part, we cancel these two lines. So the same approach, but we should have a negative here. So AX, BZ minus AZ, BX, but which is negative component. Okay, then the third component, the same approach. So we use this way, okay, from left top to right bottom. Okay, this one is positive. Okay, then rotate, this one is negative. Clear? Okay, that's a way to help you to remember. I don't know whether there is any other better approach. Okay, but I also use that way to remember this. Okay? Okay, then next section, the moment of a force vector formulation. So moment of force F about point O, you can imagine point O is like the reference point we care about, okay? Then the moment calculation can be expressed using cross product. Okay, so cross product we must follow this way. So we use the position vector R. Okay, R we can represent using as a position vector. R cross F. So give us a moment this direction. So remember from previous concept, they cannot reverse. Okay, position these two locations cannot reverse because if we reverse, that means different opposite direction. So we must use R cross F. So give us third direction vector. Okay, which is moment. Okay, interesting thing is when we apply this equation, if we look at scalar, R cross F is RF sine theta. Remember? That's a cross product. Okay, in terms of magnitude. R cross F is RF sine theta. All of you agree with this? Okay, I want you to pay attention to sine theta. Sine theta. This meaning can be shown like this. So, theta, if two vectors have certain degree, then we use cross product. Okay, then this already consider scalar times by sine theta. So we already work out its level up, moment up. Okay, you see R sine theta, which is this. So we already include the meaning to find the moment up. Clear? So this concept we can link to previous part. I asked you to remember sine theta, okay, and also should be here. We link to this part. So sine theta okay, this meaning we use the cross product. For our calculation, we already consider okay, I remember which one I want to show. This figure. Okay, using cross product, we already include a calculation to find this. Okay? So using cross product, we already find this distance. Perpendicular distance. Got it? Okay? Because we have R is scalar. Sine theta. That means we already find the moment up. Okay? Then, so we can present our moment, okay, using this form. So here is moment up. This part is moment up. So F times by moment up. Okay, so it can be shown like F times by T. So using cross product, we already find this distance. So this concept will be applied to further question. Okay, what's the advantage? Because it doesn't matter. This one is force vector. Okay, it doesn't matter what's the position vector. is as long as it pass through, okay, this vector pass through this direction. That means it can be this point, can be this point, can be this point. Finally, we work out through cross product. The answer will be the same. Can you imagine? Because finally they all convert to this. Okay? So we use a proper order of cross product. Okay, here I already mentioned. Here is a explanation. So doesn't matter which one is the position vector, as long as from the reference point, this vector connected to the force vector. Our final result will be the same, because cross product already include the meaning of sine r sine theta. Okay? You can have different theta. Okay, but finally r times by theta, the distance will be the same. Can you imagine? That's a concept to use cross product. You can have any direction, because change the direction, that means theta and scalar both length change. But theta and scalar both length change, finally r sine theta, they all convert to the perpendicular distance. Okay, you got it? They all convert back to the perpendicular distance. So, when we apply cross product, use position vector, cross force vector, finally we will get the same answer. Okay, doesn't matter we go to which one, we will get the same answer. Clear? Clear? So we will use that concept to solve later question. Okay, so use cross product, position vector, cross force vector. So previously we have a vector A cross vector B. So lastly we should list. Vector A is this one. So that's a position vector component. Then vector B is force vector. So we can use the procedure what we learned previously to work out the moment vector. Okay? Here we apply previous concept we learned from here. We learned from here. So for this calculation. Okay, so we have a shortcut, directly jump to the rearrange format. So rearrange format look like this. I know it's not easy to remember, but you can practice a little bit. Okay, we jump to easier format, that's this part. Okay, from previous, which is this part. Okay? Okay, we directly jump to here. So, the final moment we work out will be perpendicular to the plane. This plane include force vector and also position vector, because we use position vector cross force vector. So the workout direction, the moment vector perpendicular to the plane. position vector plus force vector. Clear? Okay, then if we have many position vector, many force vector, so we can work out summation to get resultant moment. This case is what I mentioned. I use this table, this desk. For example, we have a force and moment acting many different elements. But finally, if we want to see one element, other element give the effect on this element. So that's a procedure. We have many force or moment acting on the system. Then finally, we want to know one element, how it got the effect from different loading. Okay, we use this way to deal with the problem. Okay, civil system is, I already mentioned, civil system is relatively simple. Mechanical system very complicated because too many elements. So that's the reason I use the example solar, battery car, okay, electrical car. People say maintenance is easier because their element is relatively less. Okay. Then we go to this example. Determine the moment produced by the force F about point O. Okay, point O is here. Express the result as a caption vector. So we want to work out the moment. So work out the moment, we can use cross product. Okay, cross product to work out the moment. Okay, moment using caption vector. Okay, so to work out a moment, we should use R, okay, position vector cross force vector. So position vector from previous concept, as long as the position vector from the reference point direct to the force vector, then it can be used. Okay? Doesn't matter which one, can be R1, can be R2, can be R3. So theoretically, we should observe our question to find which one is easier to be determined. Okay? So from force vector, we can observe which one is easier. So right now, we look at the question. Force vector is this way. Okay? Then reference point is this way. So we, for our position vector, start from reference point and then to certain location. So we have two, for this question, we have two ways to work out position vector. One is from O to A. The other one is O to B. Okay, link. So from O to A, position vector is this value. Clear? Should I work out how to find a position vector for Rn? O to A. Just O to A. So the same approach, O to B is this component. Okay, then we have to work out force vector. So force vector, first of all, we work out the unit vector. So it's from A to B. From A to B, so we use point B minus point A. So for X component, point B is 4. A is 0. So here is 4. Okay? Then Y component, B is 12, A is 0. Okay, so it's 12. Then Z component, B is 0, A is 12. Okay, so negative. Negative. Then unit vector calculation. Okay, so this part is unit vector. So force magnitude times by unit vector become force vector. Okay, right now we have position vector, we have force vector. So R cross F. Remember to work out a moment, R cross F. So first one, we use RA cross F. Okay, IJK. Remember that's just a calculation procedure. So first one, we cancel this part. Okay, so we just use La1 is positive minus La1. Okay, positive minus La1. But 0 times by this part is 0. So we only have 12. Minus 12 times by 1.374. That's 76. This part. Okay? Then the second part we cancel this line, but we should use negative. Negative. Then 0 times this part 0. Minus 12 times this. Okay? Then the third part, we cancel this line and this line, but both of them are 0. So our calculation, we don't need to care about that. Okay, both of them are 0. Okay, so we have this part left and this part left. So here is negative. Here is negative and negative become positive. So this part is positive. Okay, so finally our moment represent using Cartesian vector is this. Okay, clear? Until this step. All okay for you? Until this step. Okay, the same approach. We use a different position vector. We use RB and cross F. Okay, for procedure they are all the same. But finally we can see the answer. They are the same as above. So it shows you, although we have two different position vectors, but it follows this rule. Okay, follow this rule. We will get the same answer. Okay? Okay, next example. Two forces, F1 and F2. So they are already shown by Cartesian vector. Determine the resultant moment they create about the flange at O. Okay, express the result as a Cartesian vector. So because they are individual force, okay, we don't need to. I should say we deal with these two forces separately. So we find out the position vector for each force, but we have to know force vector. So for F1, this direction, position vector, to be honest, the easier way is from O to A. O to A, okay? So for F2, easier way is from O to B directly. So that's the way they found position vector. So we use position vector cross force vector. So RA cross F1, RB cross F2. So it gives us two moments. So two moments plus together become resultant moment. Okay, can you imagine? That's the procedure. Okay, so RA cross F1 give us first moment. RB cross F2 give us second moment. So it gives us two moments, but finally two moments plus together. Okay, it gives us resultant moment. But calculation procedure, all of them are the same as this part. Okay, but of course, if they are not zero, okay, you should spend more time calculating the value. But the rule, they are still the same. Okay, then finally, here is relatively easy because we have 2 zeros. So for the first part calculation is easier. But second part, the calculation is longer. Okay, finally, the resultant moment can be worked out based on the value is this. Okay, Victor.